Hey again, kids. So I'm not here today because I'm going to my uncle's wedding in Florida. So, but again, through the wonders of technology, it's as if I am with you instead of being in Florida. So here's our warm-up for today. I want to practice writing the equation of a line given some information, and then another describe. So anytime someone is asking you, to write the equation of a line, then it really matters not which form. If nobody said what form to put it in, they just asked me to write the equation. So my choice is what is the most convenient. And if somebody is giving me the slope information, perpendicular, and they're giving me a point, well, then I think to myself, point slope form. Should I use point slope? Then I say, wait a second, they told me to be perpendicular to the x-axis. Well, what does that mean? Well, here's the x-axis. Here's the x-axis. To be perpendicular to the x-axis, I have to be vertical. But to be vertical, isn't the slope undefined? And I think, oh no, slope of undefined? How do I have a slope of undefined? Well, wait a second, let me go back to this information. The point -7, 3 is about right there. Can you draw a vertical line going through that point? Of course you can. There's the vertical line going through the point -7, 3. The slope is undefined, but the graph isn't undefined, and the equation isn't undefined. The slope is undefined because the slope is defined as how far did you move in the y direction compared to how far you moved in the x direction. We didn't move any in the x direction, right? But this is -7, 3. You can give me lots of points on this line. For instance, -7, 0. For instance, -7, -3. For instance, -7, 10, right? How far you moved in the x direction was nothing, but how far you moved in the y direction might have been 5 units, might have been -5 units, might have been 6 units, whatever. Who cares, because this number is undefined. But that doesn't mean the equation is undefined. You just can't use point slope because the slope is undefined. So you can't use point slope form. You can't use slope y-intercept form when you have undefined. You just have to describe it. The vertical line is where x is constant. And in this vertical line, what is x constantly? What is x everywhere on that line? Done. Right? Students make this much harder than it needs to be. What if I had asked you this question? Gosh darn it, I hate when it does that. What if I asked you to write the equation of the line parallel to the x-axis and going through this point? Parallel. Well, here's the point, -7, 3, parallel to the x-axis would look like this. You know what, that slope isn't undefined because the x movement maybe was 6 or 16 or -16, but the y movement was 0, so the slope is 0. Now I can use point slope with a slope of 0. I can use slope y-intercept when the slope is 0, but that's a little bit silly. Wouldn't you just say this is the line where y is constantly what? Not -7. The point here is -7, 3. The point here is 0, 3. The point here is 5, 3. Y is constantly 3, isn't it? Gee, what a coinkydink. Right? Practice doing problems like this. Write the equation of a line perpendicular to the x-axis passing through the point 10, 6. Write the equation of the line parallel to the x-axis passing through the point 10, 6. Write the equation of a line parallel to the y-axis. You know, like you can just practice these. These are really easy problems that kids sometimes mess up because they're thinking too deeply about it, or really thinking algorithmically about it instead of intuitively. All right, let's go on to number 2. Describe. That means write. How the graph of y equals negative 10/7 x minus 3 minus 2 has been transformed. So here are things I think about. There's my slope. Here's the x-coordinate, and somebody moved the y-coordinate from over here, but that's okay. I can still figure it out. So I think to myself, the x is 3 and the y is negative, not negative 2, right? Can you picture that? Can you picture why that is? Can you move this minus 2 and put it back over with the y and visualize what happens? I have to wait to change the color. If I want to change the color, I have to wait for this to disappear.
How'd it go?
Oh, it was good. I'm recording.
Oh.
That's okay. There we go. Oh, bother. Didn't change to a pen, did it? So anyway, y plus 2 is equal to negative 10/7 x minus 3. Oh, I love technology, but it is kind of a little bit of a dagger right now. All right, is that better? Can you tell whether the y is on this side or this side? You should be able to pull out. That's still point slope. So I don't have to graph. Nobody asked me to graph, which means I don't have to find the x and y intercept. They just asked me to talk. So I purposely made the slope a fraction, but I don't want you to immediately think the slope is a fraction and therefore flatter. It's not that the slope is a fraction. It's comparing the rise to the run. Dagnabbit. So the rise is 10. This line rises faster than it runs. Therefore, this graph is steeper, even though I have a fraction. Also, don't forget that I have a negative here. So the line does not increase over its domain, it decreases. So these are all the things I have to write about, and it would be nicer if I could write without being in a highlighter, but I don't know why I can't get rid of this bar down here with just a touch, but apparently I can't. So describe. When you describe both the point and the slope. And remember that center point, what I'm talking about is being moved from 0, 0. So where did 0, 0 go? 0, 0, moved 3 units and 2 units in the y direction. But a positive 3, remember this is x minus the y coordinate, this is y minus the y coordinate. There. So I have to say the center point moved 3 units to the right and 2 units down. The slope is negative 10/7, which means my line is decreasing over its domain. And since the absolute value of negative 10/7 is 10/7, which is greater than 1, meaning the rise is greater than the run, the line is steeper than normal. So if I was grading this on a quiz or a test, this would be worth 2 points here to make sure you talked about both the X and Y movement. And this would also be worth 2 points to being sure you talked about the line increasing or decreasing, and then whether the line was steeper or flatter than normal. All right, let's go on. So, in your notes, the most famous piecewise function. The most famous piecewise function. Piecewise is a weird word, and it is a very mathy word. It's not something, it sounds like something I made up, but I didn't. Piecewise means that your domain is chopped. And you have different functions in different pieces of the domain. So, if I ask you to graph both of these equations on the same axes, this is y equals x, this is normal, y minus 0 is equal to 1, x minus 0. However, I'm only letting you graph from 0 to the right. So when x is 0, y is 0, 1, 1, 2, 2. But here, this is y minus 0 is equal to negative 1, x minus 0. Only I'm letting you graph these not when x is 0, but when x is below 0, so like negative a half. Y is 1/2. Negative 1, y is 1. Negative 2, y is 2, and so on and so forth. There's the first piece. Starting at 0, 0, closed circle. Right? Graphing 0, 0, 1, 1, 2, 2. And then there's the second piece. Notice that this piecewise function is joined. Even though there's an open circle here, there was already a closed circle, so it looks like a closed circle. Notice that this particular function is continuous, but it has a slope of positive 1 on the right. Slope on the right is positive 1. Slope on the left is negative 1. Well, let me tell you that this special piecewise function is so famous that it has its own name and notation. This is a function. This notation here, which you've come to lovingly know as absolute value, is not an actual operator, right? You can't distribute over it, you can't combine it, it is not real. It just means that you have a very famous piecewise function. These brackets mean that I'm going to tell you what the pieces are. This is the first piece, which includes 0 and goes to the right of the domain, and this is the second piece, which is the rest of the domain to the left of 0. This is actually the definition of the absolute value function. Remember, absolute value is not an actual operator. It is mathematicians' cheating way of writing these two pieces, where the domain was chopped. The domain goes from negative infinity to infinity, but it was chopped at 0 and has one rule to the right of 0, including 0, and another different rule for the left. We are going to define this absolute value function as our parent, or our normal absolute value. normal absolute value looks like this V. And don't forget that the function, right, f of x, the range, right, these are range values. The range values are always positive because when you put in numbers that are bigger than x, you get x out of it. I mean positive, all x's that are positive or 0, you get 0 or positive. When you put in negative numbers, you're supposed to take the opposite of a negative, which is of course positive. So all x's that you put in here to the right of 0 generate positive y values, but all x's to the left of 0, any negative x, you negatize, so a negative negative becomes a positive. Notice that graphically, right, there's the x-axis. Notice that the absolute value graph is always above the x-axis. The normal one is always above the x-axis except right there at 0. So here's another picture of the absolute value function. Should have arrows here to indicate that the domain goes on forever and ever, but the range is always positive except for 0, and the special turning point is called the vertex, and for us the vertex of normal will be at 0, 0. This is what I used to call the center point, right? The center point. We now, in absolute value, can call the center point the vertex, V, for the shape of V. That's again what the actual absolute value function looks like. One rule to the right, first piece, broken up at the domain of 0, right, from 0 to the right, right of vertex, and negative x is your second piece to the left of the vertex. Now I'm going to give you the graphing form of the equation of the absolute value of x, and tell me if this doesn't look darn familiar to you. Hey, that looks just like the point slope form of a line, except for now you have absolute value bars around the x instead of parentheses. That's how you tell the difference. But guess what? What goes with the x is the x coordinate of the center point. What goes with the y is the y coordinate of the center point. It's just that what do we call the center point now? The vertex. Now, what is, before I do that, let me just write them right. We call the center point the vertex now. The slope changes on either side of the vertex. Before we got to decide this, someone decided that the slope that would be written in the equation was always the slope to the right of the center point, which again is the vertex. We didn't get to decide that, but you need to understand that if I have the minute I have absolute value, I really have two slopes. And the slope to the left is the opposite of the slope to the right. You just don't write that one in the equation. So there's an absolute value graph again. The center, this is normal, and my center point or my vertex is at 0, 0. So I would put 0 here and 0 here. The slope to the right of the vertex is positive 1. The slope to the left of the vertex is negative 1. But the only value that gets written in the equation is the slope to the right, is the special one. So 1 is written there. And of course this reduces this, or not reduces, but simplifies to y is equal to the absolute value of x. Let me erase what's on here so that you can see my, right? So here's the vertex. I went to the right one and up 1. And that's how I graph the right piece. And for the left piece, I am going to also go up 1, but I'm going to go left 1 and up 1, and that's how I graph the left. Right? Left 1 and up 1. Because my vertex always, the second piece always is a reflection across a line, vertical line going through the vertex. The second piece is always a reflection across a vertical line through the vertex. Look at all these V's, vertical line, vertex. So, when I ask you to graph and label and describe, right, so that's 3 things that you're going to expected to do. You need to graph, you need to label the way I show you how to label, and you need to describe the transformation from y equals x. I'm sorry, y equals absolute value of x. So, here's our first example. The vertex is my center point. There's the x-coordinate, there's the y-coordinate, 1, 5. The slope to the right of the vertex is the slope you see in the equation. The slope to the left of the vertex is the opposite. So, describe. So to describe, the point 0, 0 is now 1, 5. So write 1 unit and up 5 units from 0, 0. The slope is negative. So my graph is upside down. And since the absolute value of -2 is 2, which is greater than 1, the rise, again, is greater than the run. So my graph is steeper, but we say, instead of steeper, we say more vertical. Right, squeezed. Y-intercept and x-intercept. A y-intercept means you plug in 0 for x. And x-intercepts means you plug in 0 for y. But since this is not a one-to-one function anymore, because of the reflection, you might have 2 x-intercepts because you have 2 lines. So let's go find these. First, to find the y-intercept. To find the y-intercept, I'm going to go to the equation and I'm going to plug in 0 for x. Y is equal to, and I'm going to add that 5 to the other side, -2, absolute value of 0 minus 1, plus 5. Absolute value of -1 is 1. 1 times -2 is -2, and -2 plus 5 is 3. To do x-intercepts, you must use the definition of absolute value. And this throws kids off. You have to break this back into pieces. You need to find x-intercepts of both pieces. So, the first piece is when y minus 5 is equal to negative 2, drop the absolute value, because that's when that's regular x, right? And that I make y 0. And find that x-intercept. Divide negative 2, divide both sides by negative 2, and I get 5/2 is equal to x minus 1. Actually, I'm not going to drop the, let me not do this. Let me not drop the absolute value first. Let me just do the absolute value here, and you'll see why that is later. So I'm going to leave that here. I'm going to leave it here as well. And I'm going to leave it here as well. Absolute value all by itself can only give positive answers. The 5/2 is positive, so I'm okay. Now I'm going to use the definition of absolute value, now that I have absolute value all by itself, and I'm going to say either, now I'm going to do the first piece, either 5/2 is equal to x minus 1, or 5/2 is equal to the opposite of x minus 1. And if you look back at your definition of absolute value, that's what happens. At the vertex, right, you either have a positive or positive x, or in this case x minus 1, or negative. To the left of the vertex, you have negative whatever this is. And now I just do algebra 1. I'm going to add 1 to both sides. So 5/2 plus 1 is 7/2. Or here I'm going to divide both sides by a negative 1 to get negative 5/2 is equal to x minus 1. Then add 1 to both sides. And I get x is equal to negative 3/2. So I have 2 x-intercepts. So I'm going to go over here and graph the first one. So I graph the vertex is at 1, 5. Label it. The slope to the right of the vertex is negative 2, so that's down 2 over 1. The slope to the left of the vertex is opposite, and remember it's a reflection across a vertical line going through the vertex. So instead of going over 1 and right to the right 1 and down, whoops, sorry, my bad. Oh no, I did that right, silly me. Right, 2 over 1, right, to the right 1, down 2 is negative 2. Oh, should have had faith in myself. Now I have to wait until I can't draw, until there we go. Over 1, down 2. Reflection, so I go left and down. Oh snap, there's my y-intercept. Right, negative means flipped. Here's my x coordinate of the vertex. Here's my y coordinate of the vertex. Slope to the right is negative. Slope to the left is positive. I found my y-intercept, which was 3. And I found my x-intercepts, which were 7/2 and negative 3/2. The last thing I want you to do, I do want you to draw this reflection line, and I want you to give me its equation. Think about how the warm-up, I had you write the equation of a vertical line. X is always the x-coordinate of the vertex. That's your symmetry line. We call this the line of symmetry. And the line of symmetry always is the vertical line that goes through the x coordinate of the vertex. This is the, I already did this. This is my little icon for this is the describe guy. And remember, you're always describing the transformation from normal. This absolute value graph moved 1 unit to the right, 5 units up, was flipped or upside down, and more vertical. Right? Negative slope to the right and absolute value of slope greater than 1. Good? So I'm going to go back to the slide, back to the previous slide, and I'm going to do a second example. So let me erase all of this. Oh, bother. I really have to figure out how to get that bar out of my way, that toolbar down there. I'm sure one of you knows how to do it. So what I'm going to do this time is I'm going to have almost the same graph, or the same equation, a very similar looking equation, but notice that this time, instead of having the slope to the right be negative, the slope to the right is positive. So I want you to think about now, without me doing a bunch of, without me writing anything yet, I want you to picture the vertex is still at 1, 5, but the slope to the right of the vertex is positive 2 for the new one, meaning the slope to the left of the vertex is negative 2. The point is now 1, 5, which means I still, from normal, went right 1 unit and up 5 units. But this time I don't, since my slope was positive, I still open, the slope to the right was positive, I open up. Now think about this though, if you open up and your vertex is at 1, 5, how many x-intercepts are you going to find? Right? Can you picture what that is? A vertex is at 1, 5 and the absolute value opens up. Do you have any x-intercepts? I don't think so. You need to make sure your math backs you up on that. Okay? Huh? The math will show me this? What? Yes. Remember how we did the math here? Where we put 0 in for y, and we got negative 5 is equal to negative 2, absolute value x minus 1. And then I divided both sides by negative 2, and I got positive 5/2. Absolute value. Once you have absolute value all by itself, there's no multipliers around it. No multiplying, no adding and subtracting after it. Absolute value can only generate positive numbers. Right? It's the whole deal with absolute value. Can only generate positive numbers. So look what happens here. When I put 0 in for x, I get negative 5, y. I get negative 5 is equal to 2 times the absolute value of x minus 1. Divide both sides by 2. And I get negative 5/2 is equal to the absolute value of x minus 1. Absolute value, all by itself, cannot ever equal a negative. That is the math speaking to you. You were looking for x-intercepts because you made y 0. The math says, no, there are no x-intercepts. Because absolute value was equal to a negative. That's nonsense. And your math is saying, I'm giving you nonsense because what you're looking for, x-intercepts, do not exist. Now, I knew that graphically. The vertex was in the first quadrant and opened up. The absolute value opened up, so I wasn't going to have any x-intercepts, but this is the math backing it up. Now, a y-intercept I'm going to have, right? A y-intercept is when I make x equal to 0. Absolute value of -1 is 1, 2 times 1 is 2, and add 5, and I get 7. So now let's graph this. Right? I still have the same vertex at 1, 5, right? X coordinate of the vertex, y coordinate of the vertex. Slope is positive, so I open up. And remember, this is the slope to the right of the vertex. So 1, 2, 3, 4, 5. I go up 2 over 1. Draw my line of symmetry through the vertex. Label it, x equals the x coordinate of the vertex. And then flip this right across. Oh snap, there's my y-intercept. I hope it's 7. 1, 2, 3, 4, 5. Yep. Notice that I don't have any x-intercepts. Duh. Here's the problem though. I have the vertex labeled and I have the y-intercept label. I don't have any x-intercepts to label, but I have to have at least one point on the other side. So if this is 0, 7, and I want to cross here 1 unit to get to the line of symmetry, well, this is just one more unit, right? So this is 2, 7. So, absolute value graphs, the labels you must have. You must have the vertex. You must have the x-intercept. 2 of them if they exist. You must have the y-intercept. If you don't have any x-intercepts, you need to have at least 1 point on each piece labeled. Right? So over here I had the vertex, the x-intercepts, and I had the y-intercept. I don't have to label this point. You can, but I don't have to. But over here, I had the vertex and I had the y-intercept, but I had to graph this symmetric point. I used the point of symmetry to just fold it across, because of that way I got one piece, one point on each piece. Down here to talk, I still use the vertex moved 1 unit, 1 to the right, 5 up. The absolute value graph opened up because the slope was positive and was still more vertical because the absolute value of the slope to the right was greater than 1. Okay? So your homework is just like this, where for each one you have to graph, you have to label, you have to find intercepts. If there are any x-intercepts, you have to find 2. Sometimes an absolute value only has 1 x-intercept, but remember you must at least, besides the vertex, you must at least have 1 point on each piece. You'll always have a y-intercept. You always have a vertex, you always have a y-intercept. You might have 2 x-intercepts, you might have 1 x-intercept, but if you have no x-intercepts, get me at least 1 point on each piece of your graph. That's it. I will see you on Monday.